You are able to see?
Yes.
Okay. So today we will go through uh, the shared memory. Okay. Let me. So what happens with the shared? Any idea with the shared memory? What is shared memory? So basically, what we are doing in share memory, the name itself is saying that the memory is going to shared among multiple processes, right? I mean, more than one process. So there is a technique in kernel that you can create a memory and you can basically share the segment of that memory to the other process. So in that case, what will be happening is one process can write, other process can read it. Okay, so for an example, like subscriber and publisher, or the producer and consumer, right? So shared memory is one of the fastest way, I would say, that to basically to talk from one process to the other process, or I can say that in IPC mechanism, shared memory is the fastest way to communicate one process to the other process. Okay, so if you take a look at the memory map which we have, what happens there is like it is going to create another segment into the memory. Okay, and it will highlight that okay, this segment we have created, and I mean we are going to take a look that how it create a segment and how it goes and share the segment to the other process. Okay, so let's talk about CD SSM. So there is something called, let's go to the man page. So, so there is some, okay, let me just open a basic program and then I will go to, so let me just go here, mem info.c. So there is a structure called, so first of all, if you take a look at the header file, right, we have a header file specific to the shared memory, that is ssm.h. So ssm.h is basically used for your shared memory purpose. Okay, let us go and take a look at the man page of this. Okay, so if you go and take a look at the, spend few minutes into the man page and then we will come back here. So SSM CTL, SSM CTL is one of the call, basically one of the call from your shared memory perspective. So what it does, it basically it performs the control operation. Okay, so it performs the control operation specified by command on the system shared memory segment. Now, this takes basically three types of argument. One is SSM ID. We are going to see that how we are going to get this SSM ID and the commands. And the third one is the buffer structure of type SSM ID underscore DS. So SSM ID underscore DS, if you take a look here, this structure has multiple fields. Basically, this has the size of the segment, last attach time. Basically, when I mean when you create a segment, you need to attach that last detach time, last change time. So these are the basically members by which you can come to know that, even if you see here PID of last SSM attach. So this will be holding that which is the PID who has attached this segment. So lot of information you can get to know. There is another structure, something called IPC underscore permission. So IPC underscore permission, if you notice here again, you have a UID, GID, CUID, CJID. The similar one, main important is this one. Okay, so the command, what kind of command you can pass inside this control SSM CTL. So SSM CTL, you can have multiple things are there. There is IPC stat. Basically, this copy information from the kernel data structure associated with SSM ID into the SSM DS. You are, if you want to get the stats, right? So we this structure we have uh, basically this structure has the information related to your shared memory segment. So you can use this IPC set, write the values of some members of the SSM ID DSS structure. So if you want to basically set some value corresponding to this, you can go with IPC RMID. Once you create a segment, it is required that you should basically delete or remove that. So IPC RM remove ID, basically the segment will actually be destroyed only after the last process detach it. There is IPC info. You can get to know that what is the maximum segment size. So these are the data structure which is uh, uh, basically related to the system side. It's not, these are the data structure not related to your process side. These are the system related kernel. If you see here, there is something called proc sys kernel, right? You see that sys, there is a proc is a virtual file system. Inside that we have a sys system related and the kernel, and then there is a SSM RMID. So system related kernel specific shared memory things you can see inside proc sys kernel. So minimum segment size, it's always one. You can tweak basically, you, if you want this, you can tweak this based on your requirement. Okay, here again, if you see here, total number of shared memory pages current, you can basically tot ssm underscore tot, you can use this ssm info to get that how many shared memory pages are getting used, resident shared memory pages, swap shared memory pages. So we have, let's go and take a look at the program side. What happens if this call is going to be successful? It is going to return a non-zero. If it is basically positive, not a negative value. If there is some failure, it is going to return a -1. And these are the error codes. Basically, it will specify that e-fault, the argument CMD has value IPC set IPC, but the address pointed to buff is not accessible. Most of the time, you basically we see here e-overflow. E-overflow, hardly you will get it unless your system is basically IPC stat is attempted and the GID or UID value is too large to be stored in the structure pointed to by buff. So let's jump to the program, and then if I'm going to say SSM CTL, now this SSM info structure we have seen. Info structure is basically to find out system related information, that maximum ID, what is your TOT, RSS, swap, attempts, swap success and all. So if you are going to pass this structure here, right? By the way, SSM CTL, if you notice that the first argument is going to be uh, inside, the first argument is going to be SSM ID. We don't have any SSM ID, we are going to get information for the entire system. Command we are passing as a info here. Info is something related to this one. Basically, you are going to get information from the system side, system wide shared memory. And the third one was structure, buff structure. So buff structure is going to be SSM ID underscore DS. Now, once you fill this, then what is going to happen? This call is going to fill this structure. Once you're going to pass an address of this is going to fill the information, and we are going to extract the member, or you are going to extract the information from this and printing it. Now so no need to go with any special linkage here. You just have to say uh, the normal way you can compile it, and then you can say mem info. So maximum id index is 21, total is this much, rss. Now there is something called ipcs-m. Okay, so if you take a look here, basically this is dealing with the shared memory segments. So these are the shared memory segment which has been created and destroyed. Okay, so you can see who has created. Honor is showing as a Abhay. These are the key. Basically we will take a look at the key also. So key 0 0, I mean SSM ID is this one. And permission, again, when you are going to create a segment, when you're going to create a shared memory segment, you need to pass the permission also. You need to basically assign permission also. How many bytes you have allocated, number attached, number of attached, basically how many attachment to this id is there, and this status is basically showing as a destroy. Okay, now let's go back and take a look at the other thing I forgot to mention yesterday. Was if you go and take a look just ipcs. Okay, so ipcs is basically, it's going to give you, so this is not basically with the process stuff, this is from the system size perspective. Okay, so if you have any message queue available, you can see the information here: message queue id, honor, permission, how many used bytes and messages. Okay, this you cannot, so these are the information related to the system side. But when you are going and making use of mq underscore open, right, yesterday we have seen with the special kind of linkage hyphen lrt, so that information will not be showing here. Okay, so these are the basically when message send, message receive, basically the basic message queues or the basic shared memory stuff you can see here. Now let me just go to the other program. So let's go to the very first program is mem1.c. What we are doing here is we are going to create a segment, memory segment. So if you notice, we are passing a key value. This key value should be unique. Okay, so key is going to be unique one. Now SSM underscore gate, SSM underscore gate is basically, if you go and take a look at the man page, SSM gate is returns the identifier of the shared memory segment. So it is going to provide an identifier for your memory segment associated with the value of the argument key. So three types of arguments here you are passing as a key, which is going to be unique one. Size, what is the size you are going to deal with this shared memory segment, and SSM flag. So flag, basically here are the flags, basically IPC create, IPC exclusive, and then E sorry, and then there are SSM use TLB, and then SSM use. So they are basically few flags are here. SSM use, when you're going to allocate a page, huge page, basically the default for us is 4 KB. Okay, the default page size is a 4 KB. So when you're going to create a segment in memory, the OS is going to allocate one page for you. if your request is basically uh, in between one page, then it will, if your request is crossing basically one page, so based on that it will see that how many pages will be sufficient to uh, deal this request. But when you want to allocate huge page, like in GB or in say MB, then you can go and pass this type of flags there. Okay, so otherwise what will happen is like uh, your, if you are looking for a say page in GB and you are not passing this flag, it will basically, sometimes what happens, it will fail. On success, a valid shared memory identifier is returned. You're going to get an identifier. On failure, you are going to see -1. Okay, and these are the failure codes. So failure, you can see E exists, IPC create. If a shared memory exists, then it will be basically the return code, error return code will be invalid. A new segment was to be created and size is less than SSH min. So SSH mean or greater than SSM max. So you have a basically limitation here. SSM mean is 1 by default. SSM max, we will see that what is the maximum size, and no memory could be allocated for segment overhead. Permission. The SSM use TLB flag was specified, but the caller was not privileged. So a lot of things are there. You just take a look into this. Few things I just wanted to highlight to SSM, SSM all. Okay. So these system-wide limits on the total amount of shared memory. So total amount of shared memory is this much, u long. So there is a limitation that you cannot go beyond this. Okay, the system side limitation. So u long max, that means 2 to the power 24. This is the basically the limitation. Total amount of shared memory could be this much. SSM max, if you see there is a Linux version also. So from Linux 2.4 up to Linux 3.15, the default value for this limit was SSM max divided by page size into SSM mean divided by 16. This was going to be your max value.
Abhay, that
Yes.
SHM all depends on the system requirements, like how much memory we have, or is it a constant with all the Linux systems? The 2 raised to
Uh,
24.
yes, this one.
Yeah.
So this is on the Linux side. Okay. So the Linux side limitation you have.
So if I have a larger memory, my system does support larger memory, then also I can have only 2 raised to 24.
Yes, yes. So this is basically the kernel limitation is there. Okay.
Okay.
So over here SHM mean is the spelling is SHM. Is there any reason for that? SHM max is simple, right? But SHM mean is the spelling is not the regular.
Yeah, I don't know that basically why they have. Yes, it looks weird exactly that
Yes,
MNA.
might be some special purpose.
Yes. So
Here they
here
have
they see that SSM mean
yes, yes. The MNI also they have described system
MNI.
only.
Yes. So SSM mean is there, SSM MNI is there. This is basically in Linux 2.2 the default value for this limit was 128. Since Linux 2.4 the default value is 4096. This is basically the page size it is talking about. Okay.
Okay.
Now SSM mean is minimum size in bytes for a shared memory segment. So currently 1 byte, though page size is the effective minimum size. This is what I was talking about. Okay. So even if you are requesting for a 2 bytes or say 100 bytes or 2000 bytes, your page size is 4096 bytes, right? So it is going to give you a this much size. Bugs. The name choice IPC private was perhaps unfortunate. So IPC private, you can see few. I mean, though I have not noticed, but people have reported this. That's when they use these IPC private flags and all, they see few problems there. Okay, you can though you can give a try with that. Now let's go back to our program. So we have key, we what we are going to request is 8000, and we are going to, the flag is basically we are going to create this. So we are going to create the segments. Now let me see that if I'm going to see that IPCS-M, this segment is not there, right? Basically the key is this one, right? When you're going to pass a key, this key will be getting appeared here inside this, and your OS is going to give you a segment ID. So segment ID we are going to return from getting from this SSM Gate, and then he will say that who is the owner, what kind of permissions, how many bytes, etc. You will be basically come to know. Okay, now
But
yes,
for this one, how do we make sure the key will be unique? Like we will be passing one key that may be used earlier. So how
no,
do we make sure that?
you need to see this table
But
IPCS hyphen.
my program will be running like whenever the system starts or something like that. If the program is running, like it's not a manual intervention. So then is there a way such that I can look, the program can look into the things which the key is not used, it will get the key.
So there is another way. Uh, so these are the basically disadvantage, I would say, right here. What you can do, you have to write some few lines of code. You have to uh, basically you have to call somewhere this IPCS hyphen M, and then you have to basically whatever the key ID. There is something called. Let me my SSM Synchronize. No, there. Secret. I was just looking for something called, there is a no SSM attach CTL detach F talk. 9 to F talk is there. No, this will not be. Which must refer to an existing disabled file in the list that SSM get to generate a key types. So you can use this basically F talk. Okay. So if this is basically converts a path name and a project identifier to your system IPC key. So what it does, it's going to return a key for you. Okay. So few places you can see this, people use this ftalk call to get a unique key. The only thing is you again, this is an override, right? You have to pass the path name, the project ID. The path name, if you the path name should be also now this kind of a say temp some unique path name, okay, of the file name by the given path name, which must refer to an existing accessible file. So basically you are going to give a path name of a file, and then you are going to return ftalk. So there is another way, coming to your question, there is another way to basically to deal with this problem. We will see that after this SSM stuff. Okay.
Okay.
So we have a Posix based mechanism where you can yesterday we have seen message queue, right? MQ
Yes.
underscore open MQ stuff, right? Similar to that, we have a shared memory stuff also, where you can basically you have you can just go and create your unique things, and based on that your key value will be taken care. So you need to basically check this table, Kiran. Honestly saying that you need to check this table, otherwise you can go and take a make use of this ftalk, but again there is an overhead here. Now let us go and so we don't have a key 99 key 9999 which is there into our program, and this and that key is basically not existing here inside this table. So let me just go and say compile this mem1 and see. Few things, header files are missing. Let's ignore this for timing. Mem1 SSM ID is 24, it returned. Let's see that whether your table has been populated with this. Yes, my table has been populated, and the maximum byte, basically the byte it requested is 8000. This 1869F, if you will convert this to decimal format, I think it is going to be 9999. Let us check that. So this is the key is in hex. I mean we have passed a decimal value, so hexadecimal 1869F, right? You see there, this is the decimal, we have passed it, right? Now if I will go and say the decimal hexadecimal, so this is now, so this is the key will be listing here, and SSM ID you have received it. Honor is the root because I'm in root privilege. Permission we have not set it, that is why it is showing as a 0. Bytes, how many bytes you have requested. Attached, this has not been attached with any of the process, I mean that is why it is not showing. Number of attached is 0. Now few more things I just wanted to show you here is, if you go to say ps-aef, what is that, name1 cat talk 2712 maps. Okay, let me modify this program and then okay, let me just basically get an address here. So we have received, okay, we have not attached it, so once we will attach it, we are going to get an address there. So this is basically for your get. So you have created a segment but you have not attached it, okay, and we have printed it, and that is why basically if you notice here, this will exist even if your process will be terminated. Okay, it has been deleted once your process, no, it is there. Okay, so if you see, notice here, this is there. So how you are going to remove this? There is IPCS RM, or there is a SSM unlink. Both way you can. So manual way to remove this is as you can just IPCS RM you can use to remove that. Let's see another program, then we'll talk about the unlink also. So this program, what we are going to do is, this is basically, we have seen this part, that we create a segment ID, shared memory ID, using SSM Gate. Now we are going to attach this. So when you are going to attach this, there is another thing. So if you man to SSM ET, SSM attach and SSM detach, two calls. Okay, so these are the shared memory operations related calls. Now this is going to provide an address. Okay, once this call will be successful, it is going to provide an address, and so attach the memory segment identified by SSM ID. So it takes three arguments. One is the ID, SSM address, and SSM flag. So the attaching address is specified by SSM address with one of the following criteria. If SSM address is null, I mean, usually we just pass this as a null. Let the OS identify a suitable address and then attach this segment. If you don't want to do that, you have to be you have to basically have a valid address. You will have to make sure that when you are going to pass an address, that address should exist. Okay, so in that case, you have to go for the malloc, and you have to basically uh, allocate one page size, and then you can pass that address here. Otherwise you can leave this as a null. If SSM address is not null, the attach occurs at the address equal to SSM address round down to the nearest multiple of SSM LBA. So this will be basically again, yes, if you are going to get some weird address, it is going to get rounded with basically this the address which your OS looks for, it should be multiple of basically it should be divisible by 4096. Okay, that is what it. So there are a lot of problem happens here when you are going to pass this. So the ideal thing is to go and pass this as a null or zero. The SSM address must be page aligned. That is what I talk about. Now the flag is, again, you are going to attach this segment for read-only access, or you are going to just say that, or allow the contents of the segment to be executed. That means you are going to pass the permission. The caller must have execute permission on the segment. Remap, again you can go and remap this. There is similar to attach, there is a detach. Detach, it detaches the shared memory segment which you have attached, and on successful call, this is going to basically on on a successful call, the system updates the members of the system ID structure associated with the shared memory segment as follows. So return value will be 0, success on success 0, and on error it will be -1. Now, so when we go here, we are just passing as a, and the permission also we are not saying anything, it's a 0. Once this call will be successful, you are going to get a pointer, I mean an address, so we are storing this as in a void pointer. Okay. So shared area. Now this, using this address, now you have attached. So at the start of the session, what I was talking about, you are going to create a memory, and that memory will be basically a different segment altogether. Okay. Now you are going to access that memory. Now you can go read and write to that memory area. Okay, and this is what, so basically we are just writing something here, 10 bytes, sorry, not 10 bytes, it is a 40 bytes. Okay, so we are writing this 40 bytes. So integer we typecasted it, and then we are writing 100, 100, 200, 3, etc. Once you done this, then so let's run this and see.
Right. What's that IPC underscore key you're assigning to key? What's that variant?
IPC create this one.
No, above the key underscore key. So, yeah, this one.
Oh, this is Kiran, this is going to be a unique value, right? So this is here into the, okay, so let me just open this header file. Okay, VIM mem key. So mem key has a, just this is a value to the mem key. Okay, this is kind of a key.
So if you are using the same key for two processes, then it will collide, right?
If you are using to, say
So
again.
this is, this one is your created one, or it's the there in the kernel. This
No, no,
dot
no.
h.
This is the user defined. Okay, so memkey
Ah,
dot h
okay,
is a user defined.
okay, okay.
Now, once you go and just say that gcc hyphen o mem to a, so mem it has created a new segment ID. Let's see that. Yes, it has created, and this is 270F. If you just convert this to the uh, decimal, you can see the key which we have used in our program. Attach, now you can see the count here, this is attached. So now let me just ps-aef mem to that log to detach 7 maps. You have seen, you can see here, right, there is a these, if you notice here, OS has allocated one page for you. Okay, basically not one page, I think this is 2000, so two pages, right? Basically we have requested 8000, so 8000 is going to accommodate in two pages, so this is approximately two pages. S stands for uh, shared read write, and this is the shared ID, SSM ID, which you have received here, 28. This is basically saying that system 5 and 270F is nothing but uh, 270F is the key value. Okay, 270 is the key value. So it says that, okay, this is, and it's saying that, so you have the information here into the segment. So it is not basically the, in the interview, right, people ask this type of question, whether when you're going to create a when you're going to use a shared memory, is it going to use the existing segment or is it going to create a new segment? So answer is, it is going to create a new segment, it doesn't use any existing segment. Okay, now let us see, let me just say that IPCS hyphen n and then IPCS
Why was it showing as deleted in the
this
brackets?
because your program is going to terminate it. Okay,
But we have not terminated it still. Oh, we have not terminated it, right?
deleted is like nobody is using it. Okay, so let me just go here, say this has written something here, right? This has written now something, now it is deleted is uh, showing as a deleted.
There, and that is 27 in the brackets it is showing as deleted.
Okay, so basically the status is showing as a deleted. Okay, let me just modify this program a little bit and say Okay, this is 270F. Why it is showing as a deleted is smiley 00. Just a minute. And to SSM flag is SSM underscore okay. Now let me SSM underscore EX exec SM underscore exec. Let us see that modify the SSM underscore exec. Let me just remove this segment IPCS hyphen to IPCS RM. So you just go and pass 0x270F IPCS hyphen M. That has been removed. Okay. Now let's go ahead. You can see here IPCS hyphen M new entry. Now let us go ES hyphen AEF. Oh, it still is saying as a deleted. So at least permission it is available here. Execute permission has come here. This is like okay. I will check this one. I will check this why this is showing as a this should not show
Okay.
as a deleted, I feel. Because your a program has not been terminated, right? So it has just attached it and this is basically shows that what is ID dash D. Okay, I'll check and get back. Okay.
Okay.
Now, so once you have this, let me just basically provide a few details here. Okay. So IPCS is something called IPCS hyphen M hyphen I.
Abhay, one question.
Yes.
Whenever a process register for a shared memory, like get attached to a shared memory, that is added in the virtual address space, but it will be
Yes.
pointing to the same address, same physical address space in that. Only one, there will be only one copy of physical address space, but it will be multiple copy in virtual space. Is it like that?
Your virtual address space could be different, okay, based on basically the based on your
Process.
program process, right? But the
Okay.
physical address space will be same for all the multiple processes which are going to attach to this segment.
Yeah, and this lies in the address space of kernel, like
Yes,
that shared memory.
right.
Okay.
Now let me just see that I just wanted to hyphen n hyphen id hyphen n hyphen id is 29. Okay. So you can see details of this shared memory segment. Okay, how many bytes you have requested, PID is still we have seen, CPID is again same, number of attach is 1, what time it got created, detach time not set. Change time is basically showing as the same as your attachment time. So you can basically see this type of details using this command. Now once I will just delete this, you can not, though this is existing inside, but come on, this process should not exist as of now, and this is a bug. Oh, last process ID, it's a last process ID. Okay, this is not the current, basically the last process ID, which is, so it's showing that it is a last process ID. So this was the last process ID. Use this segment, and that is why you can see the entry of a process ID here. Okay, number of attach, yes, this has been removed, so number of attach is showing as a 0. Detach time, you can see now. Earlier detach time was not there because process was not terminated. The process has terminated, so you can see detach time. Now let's go back and do few more things. Mem 2b.c. So mem2b.c, what we are doing here is, see, one process has just, okay, so let me just do one thing here. This is what it is doing, is it's doing the same thing. It's trying to basically SSM ID, the key, IPC create, and then it, this is also going to attach to the segments, to the same SSM ID, and then it is going and keep reading the data which has been written to this shared memory. So this is going to be two programs. Let me just run into two separate terminals here. Let me just delete this entry from this table. I'm in IPCS RM hyphen it was 0x270. This entry has been deleted. Let me just delete this entry also. You should not basically.
Why?
Yes.
So here it is single writer, multiple reader, or there can be multiple writer, multiple readers at the same time.
You can go and do that also. The only thing is you have to make sure that the synchronization, right?
Okay.
So synchronization is again where you will be basically you have to make sure that if one, if read multiple read is allowed, but multiple write at the same segment, basically at the same address, right? Again
Yes.
it is a again it is a problematic one. So you have to make sure that if one or multiple processes are interested to read and write to that particular segment of memory, then you have to basically protect that. So you have to
Okay.
lock that segment. Okay. So now it is the user responsibility. User responsibility how he is going and putting a lock, or how he is dealing with the synchronization.
Okay.
So that we will talk about into the synchronization time. I will be when I will be just talking about synchronization, start this semaphore, mutex, other locking mechanism. We'll see that. Now mem 2a dot c hyphen mem 2a. Let me compile this also. see mem2b now if I will just go and say here mem2b and let me just run this here. So this is, so now the same two processes are going to attach to the same segment, right? So mem2b, mem2a and mem2b, right? The key we are using it is as a unique. So you can see the same SSM ID they will be receiving, and using that same SSM ID they are going to attach to that memory segment. So if this will write the updated memory, if he is going to use, he can see that the memory has been updated out. So in the mem2b what we are seeing is we are going to read the content of, we are going to read few bytes memory content to make sure that whether somebody is changing, we are going to get the data or not. Okay, now dot mem2a SSM ID is 30, this is okay. This has not been till this place, it is a 00 because there is a gate carry here. So if I will just, now it has written something there. Now let's see that it has written 100. So inside that for loop I is less than 10, what we are doing is to the 0th 100, 101, 102, yeah, we have written, and this data will be there. Okay, because this, even if I will just create it, say this has come out now, this is still reading because this has been attached, right? So this one, so both processes were attached to the same segment. One has written something and terminated, the other one is still hanging to that segment, so that is why it is able to read the memory. Okay, now if I will just go and say it, let me just go here and say that, if I'll just say that let's see that till this place it would be the previous data because it has not written. It has started writing, I mean it has written with the new data 999,000,001, so it is able to read. And now this data will be still there because the memory content has been modified with this, that is why it is able to read the older data. If I'll go and say here IPCS-M, so this is now one thing is let us go here and say that okay, so let me just go to the another program, mem4.c. So here we are going to create a new share data, so basically the SSM ID, and with the private permission. So let's see that what happens when you go and create this. Okay, and let us, okay, so in the next program what we'll do that we will let me just here do it here. Okay, probably in the next one, let me just run this. So what is the need of private? When you are making this as a private, what is the benefit of going with the private? Any guess?
Abhay, one question. Like when a process creates a shared memory and exits, even if the process exits, the shared memory will be in the kernel, right? Will be in
Right.
the, so it's a kernel. Who will whose responsibility to clear that memory? Like the user should remove it or what?
Yeah, that
Like
is the user responsibility.
even if no one is using it. Yeah.
So it's the programmer responsibility when you are creating a memory or attaching a segment, you should detach that. Okay, detach
Okay.
will happen, but you should free that. Basically, you should
Uh,
free the memory. Otherwise, you can see the entry into the table, right? You
okay.
can still that entry will be there.
Okay. Okay. Yeah.
But
Abhay,
when
when we send a message to that, it will be in the shared memory. And after reading, how to clear that? Is there any call to clear that or manually? For example, you have written some 40 bytes. So
Mhm.
if a process gets to read that, one process gets to read that, then how will it remove that? Should we manually loop to 40 bytes, clear that memory, or we have an other call to clear that what is written
No,
previously?
no, no. Memory content you cannot be able to clear that. So you if you want to clean the memory, you have to again revisit that portion and you have to overwrite that to the zero or to some other data based on your requirement.
But how would we get to know one process has written some 40 bytes and before I read another process write some 20 bytes? So I
That is
need to set previous 20 bytes, like whatever it was written previously, but I don't know how many bytes it has written.
so that is where your protection comes into the picture. Okay. So you have to make sure that if one is writing, you have to protect it, guard it. Like if I'm writing, if somebody is going and okay, I can allow the reading, but I cannot allow to write something to that to that portion of memory by some other uh, program or by
Uh,
some other process.
yeah, so it will be mutually exclusive, but here the process, like the process keeps on writing like one process or the other process, but I have to get the data written by the last process, and I don't know the size of that, right? So one process may write 100 bytes, another process may write 20 bytes, another 10 bytes. So when I want to read the data of the last process which is written. Where will I get the size or the attributes of that last written message?
Okay, so I will put another question. If I am passing a pointer to you,
Hmm.
can you tell me that how many bytes you will be able to read it? I will just pass an valid address. Okay.
Okay.
Can you tell me the size of how many byte or how many valid, I mean, how many valid address or how many bytes basically this pointer is going to provide me?
No, that we cannot tell, right? If that was the case, then passing a array to a function, oh, we could get the size. So here, if you're just passing a array pointer, it just points to
So
a.
so what is under our control into this is this 8000 bytes. Okay. So we know that 8000 bytes, the maximum memory I am going to get this using this shared memory is 8000 bytes. That means you have allocated a memory, you have basically you have created a segment ID, and once you are attaching that to the memory, your OS is basically has allocated 8000 bytes for you. So within 8000 bytes, so what you are going to get in this is you are going to get the address of the first byte. Okay. Now from first byte till 8000, you can go and read write any places. Now
Okay.
how you are going to you can segregate this also. Okay, you can segregate this. I mean, you can say that okay, first say you have 10, so this comes under what is called that. Say if I have n resources, okay, if I have n resources, I can allocate n number of processes, right?
Yeah. So
And
So
the
Abhay,
here,
the
yeah, if
requirement was like if there is a like I have three processes and I am writing to a shared memory. So the each process will come and will check whether this whatever the data is written belongs to me. If it belongs to me, I'll take out the data. So while taking out the data, I don't know the size, right? How much to take it out? So that was the question.
No, it is not like say how you will. It's not an event based, right? It's not an event based. It is not going to notify you that okay, this data is belongs to this. If you have attached, if any process attached to that particular segment, right? He will be working as a master. He can read and write. So both privileges are there. Now, it is you can basically write your program in such a way that if you are basically uh, you have now it's programmer responsibility because you have to basically implement in such a way that okay if you are writing something you can notify that particular process
Hmm.
that okay this basically you can send a signal to that particular process that I have written something and now you can you wake up read the data and then notify the others.
Yeah, I mean, like we can do it like this, right? Like, I mean, the three processes can agree on condition, like saying that this particular address will point to the current address of current valid address. So we'll get the starting of the address and we'll know the current address. Then by that we can subtract and find the size of the process, like how much was written. Or else we can agree at a particular address we'll write the size what was written by previous process, something like that.
That is what it is like again it is not the OS it is you are doing right that is you are now going into a mutual understanding that okay this is what I am going to do right
Yeah.
or you can basically divide this say if you know that okay this is the starting address right so I can say that okay this 8000 bytes is going to divide by 10 or they're going to divide by so 1000 bytes will be given to this 1000 bytes will be given to this 1000 bytes will be given to that also you can do
Yeah. Okay.
so it's all depends on how you are going to make use of that okay
Okay.
so this
Okay.
is like a chunk has been given to you now you can play with that chunk so it's your how you are going to tweak your algorithm how you are going to tweak your program it is in your hand
Okay.
so OS will be not involved in this by the way okay
So why
Yeah.
if there are no reader or writer for a segment, then why will it show in this command IPCS? Means should it not be freed automatically?
yeah
No, this command IPCS hyphen m, right?
yeah
So it
okay
is showing all the shared memory segments, and you are saying that until the in the program itself you are going and unlinking, it will show there.
No, we
So
have not unlinked it. Okay, so if you are not going to basically remove this segment, right?
yeah, but what if you exiting the program? Then also it should remove, right?
See, attachment it will be showing as a zero.
Okay.
If you are terminating your program, attachment will be zero. But still, that shared memory segment is available inside the memory because the cleanup has not been happened.
Okay. So means it doesn't mean that it is reserved, right? If some other process wants and if there is no memory, then this memory can be assigned
Yes,
to that.
yes, correct, correct, correct. So attachment is like nobody has attached to this, right? To this
Okay.
basically segment. That means few things has not been cleaned up, but the memory, the attachment segment, right? The attachment segment, which basically the pointer or an address which we have received, right? That has been freed up. So whatever the 8000 bytes has been reserved for this segment ID, now it has been freed up. But few things like this key, ID, permissions, etc. related to your shared memory is still lying there. But basically the table entry, right? I will say that the table entry has not been cleaned up. Now, uh, mem4. So if I will just say that mem4, you can see that again. Uh, 31. So private, again you can basically make this as a private also. your segment. But private, you just explore this. By the way, I didn't see any use of that. Let me just go and start it. So this, what we are going to do here is, if you see here, this is in name 5.c or name 5 dot name 5 file exists. Okay, file exists means there is an exclusive lock we have. So 31 is exists. Now if I'm going and say ipcrn -n, now if I run this, it has created, right? So exclusive, you can there are other flags. If your ID exists, it will just bail out, it will not create anyone. If it doesn't exist, you can see that, and it has basically an address here. Now if you just go and say that this program is still into the memory, so ps-aef encrypt name 5, let's see the proc 3294 maps. UFV3D94003B. Not attached, looks like. Now we have attached it. You can see a range somewhere. SFB3D94, right? This is the one. So you can see the address which you are receiving is basically the first address, this range, right? And then 2000, basically nothing is but 1000 is 496, so 8096, though you have requested 4096, 8192 basically. So 8192 bytes has been reserved for you. And now you can see this is a virtual address, by the way. Okay, so OS is going to provide you a virtual address, and using this virtual address you can go ahead, read and write to this within this range. So if you are going to cross this range, then there will be a segmentation fault. Okay, now let me quickly go to the other part. So there is something called file. Okay, this is just a system related stuff. Okay, this will not work as of now. Let me just go to the link one. Okay, BIM unlink.c. So BIM SSM create. So here in this program, what we are going to do is we are going to create a shared memory by name. Okay, like in the message queue, we will keep using the key basically, and based on that we were creating a message queue. Now similar to the named message queue, we have a named message, shared memory. So that will be again located inside device. There is a, by the way, there is a shared memory. If you see here, right, cd dev. So nothing is here inside. Okay, so when it is basically, there is a provision that you can go ahead and create your own POSIX based shared memory. Okay, now how to do that? So you need a name. Basically this name could be anything based on your choice, and then there is a SSM underscore open. SSM underscore, if you just go to that and do SSM underscore open. Yes, so this is a POSIX based calls which is used for shared memory objects. Now SSM underscore open, it looks for three arguments. One is the name of the message queue, and then flag, then mode. So SSM underscore open creates and open a new or open an existing POSIX shared memory object. A POSIX shared memory object is in effect a handle which can be used by unrelated process to mmap the same region of shared memory. Now these are the flags you can open in read only, read write, or if you are passing this flag O underscore create, it doesn't exist, it will create it. This is exclusive. If O underscore create was also specified and a shared object within the given memory already exists, then it will return an error. There is a privilege here. So you are basically passing that 666. On success, it will return a non-negative file descriptor. On failure, it is going to return a negative value. So we are going to open this, and then what is the Ftruncate does here? So we have opened a file. Now what we are going to do? What is the job of Ftruncate? Okay, I will run this program, then I will ask that what is this Ftruncate is doing here. So you are opening a file. Gate page size is, what is the gate page size? Gate page size is going to, you are going to get the page size. Okay, gate page size is a call, basically library function where by using that you are going to get the page size. So we are going to allocate, what we are going to do is we're going to truncate. If you notice here, we have received a file descriptor, and this Ftruncate basically takes two arguments. One is the file descriptor, other is the size. Size we are just passing the page size, and we are, after that what we are doing is we are basically allocating, going with the mmap with the size and with the file descriptor which we have received from this SSM underscore open. So you are going to get an address, and using that address you can go ahead and read and write. So when you are going to use this SSM underscore open or shared memory of POSIX, there is nothing called SSM underscore attach, SSM underscore detach. Okay, so in this case only reliably you have to rely on Mmap. So you got a file, you're going to map this to a particular memory address, and you're going to get that address, and now you can go ahead, read and write to this address. Okay, so let's see that. -o PC1. This needs a special linkage, I think LRT. Yes. So real time. Now once you run this, you can see a name, whatever the name you have specified, it is created here. Okay, now let's go back to the program. So this we have seen. Now let me just show it here. So this you have, basically you have, now once you go here, do a cat dev SSM my SSM, nothing is there. Okay, so what this Ftruncate does, Ftruncate is basically a call. What it does is it try to, whatever the size you are passing it here, it is basically uh, truncating based on, it is truncating the file based on the size which you are passing it. Let's see the man page. I'm not sure man page there. If truncate, yes. So if truncate a file into to a specified length. So length you are giving here if truncate, and you are giving a truncate, and if truncate causes the regular file named by path or reference by FD to be truncated to a size of precisely length byte. If the file previously was larger than this size, the extra data is lost. If the file previously was shorter, it is extended, and extended part is as a null. So what you are going to do here is, like, say you are going to restrict to 4096 bytes. Okay, basically you are truncating your file based on the size. So though we are going to allocate only, say we have opened file, now we are going and mapping only 4096 bytes or based on the page size. That is why, I mean, basically we are truncating this byte now. So your file will be open and it will be truncated by this size. Now let me run another program.
But we are not allocating any memory to that file, right? We are just opening that file.
Which one?
In the previous one, so you opened that file SHM open, and we are not allocating any memory for that file, right?
No, you are not allocating. Here we are allocating memory, right? This
Okay,
is a
so
file descriptor, right? Mmap, what it does, it maps the file content to the memory. So you are restricting that only 4096 bytes. It's going to be,
so what does Mmap does? It takes that file and will it maps the memory or allocates memory? What does it do?
Mmap, what it does is basically it, when you open a file, right? When you open it, so basically Mmap maps the content of the file to a memory. Okay, so if you see the address, we pass it as a null. So OS is going to assign a valid address here, the which address it is going to map this, and then it is going to return an address for you. It is going to return the first address, right? Say you have mapped this 4096 bytes of the file content to a memory location at this address. Now using this address you can go ahead and change. In the last class I think we have talked about the Mmap, right? So you can just, you will be getting an address by the way here. Okay, and using this address now you can go read the memory content, or you can modify the memory file content basically.
Okay.
Now if you just
So by this F truncate we can use anytime, means before mmap, after mmap.
if truncate you can use anytime. Okay, okay, good question. So to answer that, what I'm going to do, I'm going to write, okay, I'm going to write a, basically we are going to write something to the file, and let's see the behavior. Okay, whether we should use this before write or before mmap or after mmap, it's a question. Just wait, Nitish, I hope this will answer your question. Okay, so what we are going to do is we are again open, we are calling open, then we are just going and copying. So this mmap we have done. Now this mmap is read protection, write protection, and this is a shared. Now this we are copying some bytes to this address. Okay, so you're going to pass along this program, right? You're going to pass some string or something, some character, some not character, some input you are going to pass. That input will be captured here by argv1. Okay, we are trying to find out the length. Okay, we're trying to find out the length of the input, and then we are going to truncate. We are calling a truncate with the length which we have received from argv1. So how many bytes? I mean, basically you're going to say that okay, I'm not going to use say I'm going to see that okay, based on the input I'm going to truncate this file. So length you are receiving from this, and now you have used this truncated. Mmap, you are passing this as a length, though it doesn't matter for the mmap. Honestly speaking, it doesn't matter for the mmap whether you are passing this as a say length. It will be always with respect to the page size, multiple number of page size. Okay, if you are passing 100, 200, 1k, 2k, no, it is going to round it up, and it is going to see that okay, how many pages will be sufficient to uh, process this request. Based on that, it will be allocating the memory.
So why are we doing Ftruncate?
If truncate will be helpful, I mean this will not be helpful here, but this is just to basically resize it. I mean, uh, okay, let me run this and then I will show you that. Okay, hardly it matters. Honestly speaking, even if you remove it from the OS perspective, it will not matter. What OS will be doing here is, suppose this will matter only when, suppose if your file size is more than 4k bytes, right? File size is more than 4k bytes. Now you have restricted here that okay, you are going to consider only these 4096 bytes. So here in the length, or for an example, let's say that uh, your file size is, you never know that what is your what is the content of the file, right? So you read this, say it came to some 5000 bytes. Now if truncate fd 5000 bytes you are doing here, right? If truncate fd 5000 bytes, so 5000 bytes you are restricting, but the memory you will be allocated here will be 8192 bytes. So it doesn't matter, basically it doesn't matter. It only is like when you are going and dealing with not with this mmap, but when you are dealing with this say read write call, then only it matters. Okay,
Okay, okay.
so you can remove this, not a big deal. Now let me show you the read part. What we are going to do with the read is, again you are going to use the same shared memory name. You are opening this in read only. Okay, now once you read this, fstat fstat basically it is going to, when you are passing an fstat, it is going to find out the statistics related to your file descriptor. SB, if you notice, SB is nothing but a variable of type stat. So what this will be doing is, it will be trying to find it out whether the, when you are passing this, it will if stat. So if you do go to man to if stat, it does a lot of things. Okay, So if a stat structure is basically the stat structure which we are using here, we are passing as an address of this. If you see that what is the device containing this file, inode number, what is the inode number associated with this file type and mode, number of hard links, who is the owner, CID, device ID, total size in bytes. What is the total size, file size in bytes? We are interested in to this field only. Okay. So what we are going to do is we are reading this file and trying to figure it out. What is the size of the file? We don't know that. What is the, if I'm opening a file and blindly if I'm passing a say kind of a what is called that, say some number, random number, will not be able to. It may be possible that my file size is huge and the number which I pass here is less. So better to read the size, what is the file size, and based on that you pass this length here as a uh, the size content, so file size content, and then read permission. This is in the share mode now. Once you this will be success, you are going to get an address. Now you are writing, basically what we are doing is a standard output a standard output file number address, and then you are writing this to a standard out, and then we are just printing the size here. What is the size? So let's run this. We need two windows, so let's combine first to the right one, iPhone W1, and this is going to be GCC for R1. Okay, this is looking for a long, we know that R1, W1. The segmentation fault, any reason?
Yes, this.
So you pass 12 bytes, copy 12 bytes. This guy will be basically read 12 bytes, and even if you notice we have printed the size of the file is basically 12 bytes. So what you're going to do is you're going to just say that happen looks like I have passed a QD dot. Is it understanding something different?
Yes.
Some command it is okay. Last time again we have seen this type of issues. So you should be cautious when you are using this. Better pass. So we pass this 272 bytes and it read this 272 bytes. Now the size will be a matter here. If you this based on your file size, the memory segment, the Mmap will be allocating Mmap will be allocating a page. accordingly. Okay, now let's go back and see another one. So there is something called vim pssm underscore unlink. So unlink is, if you can append this program, I mean you can append this SSM underscore unlink. Now if you just say, if you're going to run this, my SSM is unlink, basically just looks for a name. If it exists, it will be successful. If it doesn't exist, it will be failure and is going to return a -1. You get it? Now I'm going to say, I think this is existing as of now. ls-lrt del SSM. Okay, so this exists. Okay, now let us run this. This is a hyphen o dot. Where is that? Oh, so the entry has been deleted. Now once you go to the cd tab SSM, not see anything there. So entry has been deleted. Now let's go to it. Okay, so let me just go back to signal. Signal is another way to communicate from one process to the other process. Right? What is signal, by the way? What do you mean by signal?
It is an event notification.
Yes. So, for an example, in real life, right? Let's say that we have a traffic signal, right? So it says something for us, right? When we as a, basically when you take yourself as a process, what do you see that? Okay, if you are seeing a red, you need to stop. If you are seeing green, you should continue. If you are seeing as a yellow, it's time to put a brake and need to stop. So similar way, signal is in the programming perspective, signal is basically it is going and notifying another process to do something. Okay, so there are default signals. Okay, so there are OS. So every OS, not only this Linux, Unix. If you go to the Windows also, they have a set of signals, reserved signals. Okay, so these signals is made for some special purposes. Okay, so for an example, let's say that if I'm going to run a program, uh, say sig1.c, very basic program, right? Now let's see that where the signal comes into the picture. This program, I'm going to run this program, say gcc-o sig1.c and say some sig1. So this sig1, it is running, right? Now this program is running. Somebody has come here and say notice ps-aef script sig1. Yes, this is there into the memory. Fine. What I'm going to do is going to say somebody is using this utility and saying that 3717. That means your other process has a signal to the send a signal to whom? So kill is a utility, kill is a program, I would say that kill is a utility. It is what it is doing, It is sending a request to do something with this PID, right?
Yes.
It is sending a request to your OS to take some action against this PID, and this matters. So when you're going to do this kill-l list, you can see what are the types. So these are the basically the signals which kill uses. So sig kill, it has sent a signal to kill this PID. That means though your program is running, another process is sending a request to take some action against this program. That is nothing but it is sent, that request is, we call it as a signal. Okay, type of request is a signal. So signal is basically made for some specific purposes. Okay, now coming back, how you're going to, so these are the if you see there are 64 signals approximately. Okay, sig hub, sig int, sig quit, sig kill. Few of them, I mean, we are going to see few of them signals are user will not have any control. Okay, so user will not have any control on few of the signals. We're going to highlight the signals, which are the signals. Okay, now
So, are these exceptions are implemented via signals?
yes,
Okay.
you
Okay.
cannot block that signals basically. Okay,
Yeah.
and I will tell you the reason behind that. Okay, why they have made it, I will tell you the reason behind that. So let's go to the next program. So sig2.c. Okay, so we have a signal function, by the way. Okay, what the signal function does, man tools, system call. Okay, so signal set the disposition of the signal. So though you are going to, so what we are going to do is you are going to overwrite. So corresponding to signal, if you notice here, there is a sig number and there is a sig handler. So there is a sig number and there is a handler associated with that. Okay, so OS knows when you are going to say, when my last program, in the last, we were running a program, and when we send a signal, OS knows that what is the signal handler associated with that. Okay, with this, so kill uses a number, and then that's it, right? Kill was using a number. Based on that number, your handler was taking an appropriate action. So handler, the job of the handler was to kill that program, so it killed it. Now here in this program, if you don't have a handler, let me specify. If you don't have a handler, then what will happen? Say you, I mean, we are going to use a SIGINT here. Okay, we're going to use a SIGINT, and there is a SIG hand which is based on the user specific. Okay, that means you are going to override the SIG handler. So OS has a SIG handler already implemented there internally. It knows that based on this signal what I have to do. Now if user is going to override it, the OS will not be taking an action. So the handler will be called based on, if a handler is there into your program for that particular SIG number, then that handler will be called. If a handler will not be there, what will be the handler OS knows, then it will be taking an action based on that handler. Okay, so let's say that we have a SIG hand here. Now we have written a handler here, and this is the SIG. Now we are just printing an interrupt signal received. So this program, we are running an infinite loop, and let's see that what is going to happen here. So we all know that this is going to run an infinite loop, so it is going to run forever. Let's ignore this warning for timing. C2. So this is running, by the way. Keep on running. Let's see that. Uh, hyphen A here, grid. What is the sig2? So sig2 is there now. If you remember, we have passed a sig int, right? Sig int,
Yes.
interrupt. Now, if I'm going to say here, say control C. Control C, pressing control C is nothing but it is going to generate that signal. Okay. What is this? Interrupt signal received. Some junk character don't, I mean, ignore this. I think some key has been pressed from my side. So now if I will do this control C, which is nothing but it is generating a, oh, my key has been stuck there. Let me, okay. What is this? Looks like some key has been stuck. Just a minute. Let me just. So if you notice here, this is what I was trying to highlight. Interrupt signal received. So you have a handler written into program. A, let me run this again. So this is running. Now if you're going to say here kill hyphen L, kill hyphen 2. Oh, sorry, let me just see the process ID of this sig2. Okay, this, so another one was still running there. So kill hyphen 2 is nothing but sig int, right? This is the handler we have used inside this. So this is the sig number, and we have a handler, user defined handler, right? So if I'm going to use this and say 3796 37, what is that, 3738, that was the old entry here. So if you notice here, interrupt signal received, your program has not been terminated, still it is running. Similar way to just using your again I have a problem with my control C, so I was trying to ignore that. Okay.
Wait, what is the difference between the interrupt and signal?
What is the difference between, there is a huge difference, right? Signal is just a notification. So signal is just put a break, so it just send a command. Interrupt is a very big thing. Okay, so you can have a hardware interrupt, you can have a say. So signal is related to your software side, by the way. Okay, and your sig handler is already implemented there, and it is made for some specific purposes. But whereas your hardware
But
side,
signal is triggered by hardware, right? Like by user input, like keyboard and mouse or printer. It is triggered by hardware. It's like that.
you can generate a signal using here some key combination like control C, control D, control Z, right? So these are the interrupt basically, right? Now if you are talking that interrupt, so these are the interrupt you generated, right? So these interrupts, when you are pressing any key basically, then there is an interrupt happened, right? There is a basically there is a and when you press a control C, the signal goes to your OS. Now OS will be taking care that what I need to do with this. So it knows that okay, it interrupted. Based on that, there will be handler, and it will be taking care of that particular signals. You cannot say that signal and interrupt are same, but yes, because of an interrupt, due to an interrupt, something
Okay, like
happened.
signals are implemented via interrupt. Like the interrupts are handled by OS, and OS will send a signal to process. It's like that.
You can say that. Yes, you can say that. Your handler is basically the SIG handler here.
Okay. Okay.
So SIG hand here is the SIG hand. We have overwritten the INT. SIG INT we have overwritten. So though we are pressing a control C, nothing is happened. But if I will just say, if I will ignore this for time, let's say that if I will ignore this and then say no SIG2 dot C. Now say if I go SIG2, this is infinite loop. If I will place a control C, this is terminated, right? But if you have a overwritten signal handler here, right? Because this now you are saying that okay, SIG INT I will take care. So you are taking care of what? You're taking care by just a print. Now if you are just running this and then saying that SIG2, if you are pressing a control C, saying that interrupt signal received, but if your program has not been terminated because you have overridden SIG handler. Again, if you press a control C, right? And the similar way to basically PS-A here. The other way to just three nine zero zero signal received. Program has not been terminated, so you are now let's see that, or you can do with this. If you are going to say that control D, control Z is nothing but a stop mode. So this signal OS knows that okay, I need to stop this program. It has stopped this program. Now let's go and see the other one. So these,
can I override this control Z handler?
yes, I will tell you that which are the handlers you can
Okay.
override and which are the handlers you cannot override. Okay.
Okay.
So let me just go to the SIG set one.c. Okay. Now in this, okay, so let me say that there is a SIG set underscore t and let's see that whether this is there or not. Most of the signal related stuff you will not be able to see inside the man pages. No, it's not there. SIG set. SIG set. Yes. Oh, SIG set. So this structure is not there. Okay, so this is basically SIG set is a structure. What you're going to do with the SIG set, it is going to basically have set of signals. Okay, So what we are going to do here is, if you notice there are few signal related function we are using here. So sig empty set of signals will be there. Whatever the set of signals, we can see all signals will be part here. We are just going and making, we are calling as a empty set. So basically we are emptying this. So if any signal will be set, we are just saying that, oh, you do that sig empty set. If you notice here, sig empty set will be there. Sig empty set, sig empty set, where is that? Sig empty set, yes. So sig empty set, these functions allow the manipulation of Posix signal sets. Initializes the signal set given by set to empty, with all signal excluded from the sets. So basically it is used to initialize the signals. Now we are adding signal to this set. So which is the number we are adding? We are adding sig1, signal number 1 we are adding to this set. So this set have only one signal as of now. If sig add set, if you are just taking a look, it is used to create your own type of sets basically. Now what in this program, in the coming programs, what we are going to do is we are going to create a set of our own signals. Okay, sig add set, sig add set, add and delete respectively signal numbers from set. So we are adding a signal number 1 to this set, and then signal sig add set, signal number 4, sig proc mask. This is where you are saying that you are going to block, you are going to set some mask. Now sig proc mask is another uh, function which is going to say that you are going to mask this signal, or you are going, basically you are going to say a block or unblock this signal. Sig proc mask is not there. Sig proc mask is here. Yes, here it is. So sig proc mask is used to fetch or change the signal mask of the calling thread. The signal is set of signals which delivery is currently blocked for the caller. So if you notice here, it is going to take two basically arguments. Three arguments. One is the blocking, the other one is the set, and the third one is the old set. So old set, we don't have a old set, we are just passing it as a null, and then we are just printing that send me signal 1 and see the effect now. Again, the second one, sig proc mask, sig unblock. So we are unblocking it, and the same set we are using, and we are running an infinite loop. Now once you run this, sig 1 for sigma success. Now if you see here, sig 1 4 are the signal which we have added here, kill -l. So 1 is sig hub, 4 is sigin, legal instruction. Okay, now ps hyphen, how you are going to generate this? If you don't know the equivalent key of that, then the best way to set one, best one is to use the PID and then say that kill hyphen 14083. Nothing has happened, it has been closed.
Job
Abhay, can a process create signal?
Can a process create signals? Uh, Signals are already there available into the OS side. Only thing is you can basically this
I
process,
mean,
right?
send a signal, like existing signal.
You can override the signal. This is what I was trying to highlight, right? So your process signals are available from the OS side. Say all signals are there. What a process can do, process can go block or unblock that particular signals.
I mean,
That is what you.
can it trigger a signal?
Yes, you can trigger a signal, right?
I mean, the process, or only a kernel can trigger a signal.
How you are going to trigger a signal from the process? You tell me.
And I am asking, I don't know. Like,
Any
is
way
there a
that
command?
any way to anyone any. Yes, you can do that. There are the ways, right? Say whatever the utility we are using, right? Say you can inside a process, right? You can say that send a kill command, kill SIGHUB, right? And the PID. So you are basically sending a signal by one process to kill the other process. Whatever the stuff we are doing it here, right? This is another process, by the way, right? If you are running something here, that means this you are doing inside some process, correct? The cell
Yes.
is a process for us. Now
Yes, okay.
this process is doing something or it is sending a signal to some other process uh, by PID, right? So that it can be doable basically.
Then will it not be a security issue? Like one process can kill other process? Like,
Right. This is a security issue, right? This is a security issue.
So
So,
this is handled by OS, right? Even if it is sending, it is not going directly.
so few things you can overwrite here. That is what, right? Say few things we have overwritten here. That is why, if you notice, people go with the daemon. If you hide something that user will not have any intervention, you can say that okay, I am going to run this as a daemon. So there will not be any control over there from the user side. You can kill anything, by the way. Okay, by the way, it is not like that. Okay, my the first process is init one, so I can go ahead and kill the init one, init process also, right? That is possible. What will happen? Only thing is your kernel will again, the init will respawn it basically again. There will be impact. Yes, definitely there will be impact. But yes, what happens is like if you see in the field or if you have any live devices, you when you're going to use this say some utility kill hyphen something, you'll not be allowed basically. So it allows only to the root user. So you privileges you can set here and there, but that is doable, I can say. So again, this key is a problem creating for me. Okay, so I have just so this is how you can basically
But at the OS level also we can do something to protect, right?
voice level.
Yes, kernel level means we can go and do something that this uh, process only can generate kill requests, right? Because these processes, they are not sending direct signal, right? If you are doing kill, it is going to OS, and then OS is the mediator here, right?
So if you do a man to kill, okay. So kill is a basically if you see this is a function, right? Kill sends signal to a process. So it is sending signal to a particular process. And the main thing what it is looking here is the PID, which process you want to kill and think. Now if you see here, few things are here. If PID exists, then definitely it will kill.
Mm.
Now There are exceptions. Yes, you can go and permission. You can set the permission also. Sig is sent to every process for which the calling process has a permission to send a signal, except for process one. So there are the permissions which you can override it. Okay. I will tell you that which are the signals user has user can override and user cannot override. So sig set 3.3.secret. Okay, so this what we are doing here is like, let me just say that we are added some few signals here, okay, to the sig add set. Now we are printing that which are the signal has been blocked and which are the signal has not been blocked. So it is checking that check blocked underscore sig is a function, user defined function basically. Now sig proc mask. Sig proc mask is a function, again you are calling with a block and null and the set, basically you are passing an address, set address, and once this will be done, what will happen, it will be basically this will be set with uh, the enable or disable things. Now using this you are going to sig is member, that means if signal is set you're going to return a true value. If it is false, if signal is not set, then it is going to return a false. So you're going to say that signal is set means the signal is blocked. If signal is not set, then it is unblocked. And this is what you can basically you can use this function to find out whether the signal has been blocked by, or whether a signal is blocked or signal is not blocked. So few we are added here, 1 4 we have added here block. Again we are adding a 2 as a block here and see what is happening. One is blocked, 4 is blocked, and then we blocked 2 also after that. So if you notice 1 2 3, sorry, 3 is not blocked, 1 2 and 4 is blocked. Now if you are going here and saying that, see, this is es-aef encrypt, so set 3, still 1 1 is blocked, 4 1 5 3, 4 1 5 3, nothing has happened. Now 2 is also blocked, so it will just ignore this. 4 is also blocked, so it is ignore this, but 3 is not blocked. So if I'm going to use 3, there should be some specific action which OS will take, right? And it has say that okay, it is a quit command, and then yes. So if you just say that man, sorry, what is this? Kill 3 is the sig quit. It is a, so it is quit. Forcefully you are doing that. Now once you go to sig set 4.c, 6 set 4.c, what is happening here is like same program, but 1 and 4 we have added. Now we are adding this sig add set to 2, and again yes. Now if you run, I'm going to ask, yes.
One doubt I have in this one. You have that big empty set right in middle
Mm-hmm.
after that block. So will that not clear everything? First you added one, then you added four. So
Right, right. Mm-hmm. So that intention is to show you that things, okay?
no, but in the previous case also I have done the same thing, but it had not cleared right. It also
Okay. So previous case, what? What is the difference? Sig empty set, S set. Okay.
So in this case, if you run over there, only SIG2 should be blocked and other should be removed, right? 1 and 4. But when we were running the program, 1, 4, 2 were also blocked. It had not cleared.
So it will be getting cleared when you are going to do basically when you are going to say use the sig proc mask. If you are going to mask this, then only it will be taken care. Otherwise, once you set these signals, right? Say sig empty set in between if you are using this sig empty set is not going to do anything. That's what the intention to so. So in this program, if you notice what we are doing here is we are using a sig empty set here.
Yes.
Sig add set. Now the third and fourth program, the only difference is sig empty set, sig add set we have used, sig proc mask. So sig proc mask we are using sig set mask. This we were not using inside this the previous program. If you notice here, let's go and see your third program. Sig block, yes, fine. Set mask. Set mask we have not using. So if you are ORing with a set mask, that means it has emptied. Now you have to mask it, then only when you're going and using a set underscore mask, then only the latest will come into the picture.
So in this case, the latest was also coming into picture. It 2 was also blocked.
And the third one?
Actually, in the output, 2 was not actually blocked. If we run the set 3, right, 2 was not blocked
So
actually.
2 was blocked. 2 was blocked.
2 was blocked, right?
2 was blocked because
Yes.
2 was blocked because if you are ORing with sig underscore set mask, then these two entries will be gone. That is what in the fourth program I am trying to highlight. So you need to understand when you are adding a sig empty set in between, what needs to be taken care. Okay. So if you notice here, sig block sig underscore set mask. Sig underscore set mask is going to override now. It's going to override. Now, if you are going to run this gcc -4 set 4, say one was blocked, 4 was blocked. We came to the empty set, and then what we said that sig add set signal number 2, and then sig proc mask with set mask. So set mask, what it does, it is basically going and setting a new mask. So it is basically a new entry now. So all the entry will be, all the signal where it will be there, it will be masked. All that mask means it will be deleting basically. So it will be uncleared. It will be basically clearing the bit. It will be clearing the set bit. So once this bit will be cleared, now you are going to add this signal only. That is why this 4 program, if you can see, the only 2 is blocked.
Okay,
Whereas
the set mask will clear, is it? So here, set mask will clear the previous one. That's what you're
yes,
saying.
yes,
Then name is confusing, right? It should be clear, not set, right? Sig clear mask.
set mask means yes, it's set mask is basically to clear the bits, clear the bits. So if any signal is set, it will just, what it will do, it will be just
Can we
what
print that sig set mask what it is? Bitmap of sig set mask.
the value you mean?
That one want to see like if it's completely 1 or 0, whether it is setting or clearing, because when you're setting this 2, only setting the 2 and clearing the other, so it should be uh, 0. So 6 set mask should be 0, I guess. So that's the case, then it will clear the previous one. Setmask. No, Setmask. Yeah.
So Setmask, okay. Let us say, let's print both, okay. Setmask will be one, I feel. We have not printed it. See that. Four, two. Okay, so this size 2.
Setmask.
Setmask is 2. It's a macro basically. You can check in man page.
Okay.
Now quickly let me just go to the set file. We'll wind up. So this program, what we are doing is we are just sig fill set is another one. Sig proc mask, sig set mask. If you notice here with all the sets. So we are not basically we are not here. What we are doing is we are not masking any signal here. Okay. What we are doing here is we are going and seeing all the 32. We are running a loop till 32 and we are trying to figure it out which is the signal which has already been blocked and which is not blocked, okay, for the user. So basically from the system side, so user has not fill any data to this set, so it is going to take all the data sig fill set. We have not added sig add set anything to this, any signal to this, so it's going to take all the signals and we are going to check which are the signal is blocked, which are the signal is not blocked. So let me go here. If you notice here, signal 1 can be blocked, signal 2 is blocked, signal 9 you cannot override this, okay. Even if you just try to pass this, your OS will be basically simply it will ignore this, okay. If you are going to add this to your set and trying to block this, OS will simply ignore this. Same will be applicable to signal 19. So few signals we don't have a control. Being as a programmer, we cannot have a control there. Now, if I'm going and say that, say you run this to 63 and see. (32) and 33 signals are also not blocked. 9, 19, 20, 9, 19, 32 and 33. So now if you go and say that kill -l, let's see the signals. So sig 9 sig kill is the one which you don't have any, I mean basically you cannot override that, and then 19 is a sig stop, 32 and 32 sig, I need to see where is 32, 32, 31, 32 is not, 32 and 33 entry is now there, looks like.
It has been masked that it will not list also.
Yeah, we need to see that what is pointing to 32 and 33. So minor killed will not have that. Uh,
I think those are real time signals.
looks like these are the 31, 32 and 33 is not there. So let's see that what is 32 and 33 is pointing. So the idea here is to show is few signals we don't have a control. Even if we will try to control it, will not be. Okay. So this is how you can basically go and mask or unmask the signals. Okay, so let me stop it today here, and I will share all these materials to that share code.
One question, like if you want to send a signal to another process, we will be using the kill function, right?
Right.
Okay. Okay.
There are the other utility also.